All right, welcome. Today we're going to pull back the curtain on a really cool engineering problem that honestly makes the modern internet work. We're talking about unique IDs. How do you create a unique number for every single tweet, every online order, every anything when you're operating at a global scale? Let's dive in.
Just stop and think about that for a second. Every single interaction you have on a huge platform needs its own special number. We're talking about systems that have to spit out tens of thousands of these IDs every single second, from data centers all over the world. They have to be totally unique, of course, but also generated lightning fast. So, how in the world do they do it?
So where do you even start with a problem like this? Well, the first idea that probably pops into anyone's head is the most obvious one. Why not just, count?
If you've ever messed around with a database, you've almost certainly used an auto-increment key. It's simple, right? The database just hands out the next number in line. 1, then 2, then 3. It's perfectly ordered, and it guarantees no two rows get the same number. For a small app, it's pretty much perfect. But what happens when your little app goes global?
See, on a single server, life is a dream. There's one single source of truth for what the next number is. But in a distributed world, you might have hundreds of servers all trying to create new things at the exact same time. How do they all agree on the next number without stepping on each other's toes? This is where our simple little counter starts to get really complicated.
Let's dig in and see exactly why this simple idea completely shatters the moment we try to scale it up. To stop two servers from accidentally grabbing the exact same ID, the database has to put a lock on the little file that keeps the master count. So, while one server is reading the number and updating it, every other server has to form an orderly queue and just wait. This works, you get no duplicates, but you've just created a massive traffic jam. It totally defeats the purpose of having all those servers in the first place.
In the code, you can enforce this one-at-a-time rule with something called a synchronized block. You can basically think of it as a digital bouncer at a club door. One request gets to go in and grab a number, and everyone else waits outside until it's done.
And hey, it works. The output is a perfect, clean sequence, one after the other, no duplicates in sight. But, as the engineer Ian Kent who built this example points out, the performance is just terrible. So, we've solved for uniqueness, but we completely killed our ability to scale. We need a much, much better way.
Okay, so asking the database for one number at a time is way too slow. What's the next logical step? Well, why not ask for a whole bunch of them at once? This is called batching, and it's a super clever idea that just so happens to be hiding a really nasty trap.
Now, the logic here is actually brilliant. Instead of bugging the database for every single ID, each of our servers will ask for a big block of them, say 100 at a time. Then it can just hand out those 100 IDs from its own memory, which is super fast. It only has to go back to the slow database once every 100 requests. This should solve everything, right?
The code itself seems perfectly reasonable. When the server notices it's running low on its local stash of IDs, it just makes a call in the background to get a new batch. I mean, on the surface, this should work flawlessly, but there's a fatal flaw hiding in the timing of it all.
The result is an absolute disaster. The system is spitting out numbers like 11, then 1, then 41. It's burning through the ID space at a terrifying rate, using maybe one or two numbers from a batch of 100 before grabbing a new one. In just 100 requests, it's already used up IDs all the way to 991. What on earth is happening here?
The culprit is a classic programmer's nightmare called a race condition. What was happening was that multiple requests were hitting the server at the exact same millisecond. They'd all see that the server was out of IDs, and they would all scream for a new batch from the database at the same time. The server would get, say, 10 batches back, but it would only use the very last one it received, effectively throwing the other 900 IDs in the trash. A complete mess.
Okay, so clearly relying on a central counter, even a fancy batched one, is just asking for trouble. The industry needed a completely different way to think about this, an approach that didn't require all the servers to constantly talk to each other. And that is exactly what Twitter came up with.
So what do we actually need here? Well, we need the IDs to be unique, that's a given. But we also really want them to be sortable by time. And of course, they need to be efficient. Now, other methods like UIDs are unique, but they're random. You can't sort them by date. Ticket servers give you both, but you're right back to that central bottleneck problem we tried to escape from. The only solution that ticks all the boxes is Snowflake. And this is the absolute genius of the Snowflake design.
It doesn't ask anyone for a number. Instead, every single machine builds its own unique ID from 4 distinct parts. The biggest chunk, 41 bits, is just the current time in milliseconds. That right there automatically makes all the IDs sortable by time. Then it cleverly bakes in a unique number for the data center and the specific machine it's on. This makes it impossible for 2 different machines to create the same ID at the same time.
And that last little piece, the 12-bit sequence number, that's the final magic trick. It allows every single machine to generate up to, get this, 4,096 unique IDs within the very same millisecond. It's this decentralized approach that gives you mind-boggling speed without any central bottleneck.
But a design like Snowflake isn't just a clever algorithm. It's really a window into a much broader philosophy in system design. You have to build for resilience.
A truly strong system is designed with the core assumption that things will go wrong. Modern systems use tools like message queues to make sure that if a service is down, the data just waits safely for it to come back up. They use patterns like circuit breakers to contain a failure in one small part of the system so it doesn't cause a chain reaction and bring down the whole show. Snowflake's don't talk to anyone design fits perfectly into this mindset.
This code here really nails the core idea. By decoupling components, which just means they don't have to talk to each other directly all the time, you build systems that can take a punch and keep on going. The ID generator doesn't need to check in with the database, so even if the database fails, new IDs can still be created without a problem.
So, we went on this whole journey from a simple counter that just couldn't scale to a clever but flawed batching system and finally landed on an elegant decentralized solution like Snowflake that powers so much of the web today. But it makes you wonder, as we look toward a future of even more decentralized networks, maybe the metaverse, what new challenges will pop up and what will the next brilliant solution for identity look like?